Okay, so we're looking at evaluating the derivatives with function notation. And all I'm going to do is just use proper notation here. So I'm going to take the derivative of y. Well, this first part is just 6 times a function. So we're going to take the 6 as a multiplier, and then we're going to write the derivative of f. So nothing crazy there. The next one, though, has a function to the 4th power. So there's a chain rule here. We have to deal with this 4 first. If you really want to, you can think of it written this way. Pull the 4 on the outside. Well, then what happens? The 4 comes down, and we're going to take one away up top. And the chain rule says take the derivative of the outside function, keep the inside, and then we have to multiply by the derivative of the inner function, which is g prime. So I will guarantee you see a good amount of questions like this on the AP test, as well as our quiz and test in the future. All right, the next one. This one's much more tricky. Notice it's not addition, it's multiplication. So we actually have a product here. We've got u and we've got v. So I have to apply my product rule. But then within that product rule, there's a chain rule part. So I highly recommend setting up your two pieces. What is v? Or excuse me, what is u and what is v? I'm going to write v with the 4 on the outside. So we recognize that that is a chain rule. That doesn't look good. And now we have to take the derivative of each piece. So I'll try to color coordinate this a little bit. We know the derivative of u because this was basically u here. And then the derivative of v is the same thing that we just did right here. It's the chain rule again. So I'm just going to rewrite that. And then we're timesing by the derivative of the inside. So this is not going to look very pretty, right? It's going to be a fairly long derivative, but what do? We take the derivative of the first using the product rule, derivative of the first times the original second. And I think instead of writing the 4 in the upper corner, I would put the 4 right above the g. So there's the derivative of the first times the second, plus now we have to do the original first times the derivative of the second. And then the second is this whole big chain rule piece. And I would, even though it's multiplication, I would put big parentheses around that. And I'd call this g to the third. You could put the 3 above it like it is here, or you can put it right above the g. It's the same thing. And then we're timesing by the derivative of g. And I would stop there. You could pull out a g to the, no, yeah, you could factor out a factor of 2 and a g to the third, but that's going to make it look even worse. So leave it. All right, that's probably the trickiest one. And then number 3, this is just the quotient rule. We've got a function u divided by a function v. And I'm hoping on this one, you don't need to show your work. Because what do? We take the derivative of the first. Well, the derivative of the first is just f prime times the original second. And then we always subtract. And then it's the original first times the derivative of the second, or the bottom. And then the quotient rule The only thing that makes the quotient rule different than the product rule is its subtraction, and we have to divide by the original denominator squared. And you could put the 2 here, or you could put it right in there. Okay, and then the last one, this is a function inside of a function, f of g. This is just our chain rule. You take the derivative of the outside. And I just kind of remembered I was highlighting quite a bit when we introduced the chain rule, so if that helps you. The outside function is f, the inside function is g. So if I take the derivative of the outside, that's f prime, keep the inside exactly the way it is, and then multiply by the derivative of the inside, which is just g prime of x. Okay, so hopefully that's a really good confidence builder on, do you know the product rule, quotient rule, and can you recognize the chain rule when it's mixed into different problems? That's really where we need to be at right now. Okay, this was just the answers. Really quick, you don't have to write these down, even though it says write. Just see if you can, from memory, do you know what the 6 derivatives are? See if you can go through that, and I'll give you about a minute to just kind of quiz yourself in your head. All right, let's take a look. Derivative of sine is cosine. Derivative of cosine, negative sine. Derivative of tangent, secant squared. Now, I always think of this. Derivative of cosecant starts with a c, so it should be negative, and then it's always cosecant, cotangent. Derivative of secant starts with secant, and then secant tangent. And cotangent's derivative is going to be negative because it starts with a c, and then it's cosecant squared. So those should be mastered. You're going to, on the AP test, they're going to expect that you know those. All right. You don't have to write this. This is just a quick introduction. We're doing more with the chain rule, and I hope you really understand the importance of the chain rule. We are spending all day today working with the chain rule. We did that on Monday and on Wednesday. So we spent 3 full days on the chain rule here. Those of you that didn't do the work on Wednesday, you definitely need to go back through and watch the video and do the Delta Math homework. Okay? All right. So what is the chain rule? It's when we have the composition of a function inside of another function. And the saying is take the derivative of the outside, leave the inside, and multiply by the derivative of the inside. That's the process that we take. So my goal is to try these. And these two are a little tricky. We call them a mental challenge, more of we want you to try to do this without showing a lot of work. Meaning, is there anything we can do to make this a little easier to start? So I will have you write these two down. And the directions are, can you find the derivative? Well, one of the things that you have to remember in calculus, if we don't like the form that it's in, can we rewrite this so it's a friendlier version? Because right away, I bet a lot of you would see this and say, ooh, it's a quotient rule. Now, you can do the quotient rule. You can definitely do the quotient rule here, but you don't need to. Here's why. Remember how if something is in the denominator, we can pull it out and make it a negative exponent? Officially, this little negative, there's a 1 here because it's the first power in the denominator, but when I pull it out, it could be written right here. But then I also want you to recognize that that negative 1 can be written on the outside of that. So we're doing the sine of 2x to the negative first power. Well, now I hope you can see a little more friendlier. We have an outside function. My outside function is raising this to the negative first power. Now the 5 is just a multiplier, so that's just part of it. And then I've got my inside function, which is sine, but then there's an innermost function inside of there too. So we have a double chain rule on this one. All right, so what would this look like? Watch my notation. Y prime. Notice all of this is equal to, that just means equivalent. All of this is the same step. It's all just algebra. When I do the derivative of the outside, the negative is going to come down. Negative 1 times 5 is negative 5. And then what do? We take 1 away. So negative 1 minus 1 gives me a negative 2. So there's the derivative of the outside. Keep the inside exactly the way it is. Don't change that. And now I have to do my double chain rule. So now I have to multiply by the derivative of sine. Well, the derivative of sine is cosine. But since this has an inner piece, we're going to keep the inside piece on that. And then I have to multiply by the innermost inner layer, which is the derivative of the most inside piece. The derivative of 2x is 2. And then we would be able to clean this up. So here's what I notice. The sine of 2x is raised to the negative second power. So I'm going to take the sine of 2x and I'm going to raise it to the positive second power. And again, we could put the 2 here, or you could put it on the outside up here. And then I've got some constants. I got negative 5 and 2. Well, negative 5 times 2 is negative 10. And then notice this technically is cosine to the first power, so that's a positive exponent. It's going to stay on top. And that's as far as we can go. Okay, now keep in mind you cannot reduce this 2x and this 2x. And the reason why is they're protected by the cosine and the sine. So that one's a little bit more tricky. We definitely had to show some work for that. You can't fully do this in your head. But this one you might actually be able to do in your head. Now, notice it has the square root. I'm going to rewrite this algebraically, so I'm not using a prime. This is just the equivalent expression. Taking something to the 1/2 power is the same, or the square root is taking it to the 1/2 power. Those are equivalent. Well, now this screams chain rule. Inside outside function. What is my outside function? That's the 1/2. And then the inside function is just the polynomial. So this is a single chain rule that is actually quite friendly. All right, so now I'm going to use my notation. Take the derivative, so the 1/2 is going to come out in front. We haven't done a lot with radicals yet, so this is a good practice. And then what do? We always take one away, so I want to subtract the creative form of 1. So 1/2 minus 2 over 2 gives me a negative 1/2 in the exponent. There's the derivative of the outside. Keep the inside, and then I have to multiply by the derivative of the innermost piece, which is right here. So this is just two quick power rules. 2 comes down, multiplies by 3, and then the derivative of minus 2x is just minus 2. You don't need to put the 1 there. How many people are bugged by what I just did? You should be. I did this on purpose. Something's wrong with what I did. I didn't make any mistakes, but I forgot something. I did that on purpose. Right now, if I read this, this is everything here times by -6 and then minus 2. That's not the way the chain rule goes. You need to have parentheses. So we talk about proper notation, and that's one of the pieces here is you have to make sure that this is in parentheses. Right now, that could be an answer, or what if I rewrite this? I have the fraction 1/2. But then I've got this entire piece to the negative 1/2. Well, the negative is going to put it down in the denominator. The 1/2 is going to turn into a square root. So it's going to be a square root in the denominator. And then officially, I would take this 6 minus 2x and times it by the numerator up here. Timesing it by 1 doesn't really do much, so I really don't even need this 1 right here. And I could just write 6 minus 2, or 6x minus 2. And you could, I guess if you want, you could divide this 2 into both of these. So this could really be a 3, and this could be a 1, and this would be a 1. So a better written, reduced answer would be right here. So if you're looking in the back of the book, or if it's a multiple choice question, it would be the green one. If it was like a short answer test and it didn't say simplify, you could have stopped right here. All right, I hope your confidence is building with the chain rule. Because what we're going to do now is we're going to apply the concepts that we've learned in the past and see how the chain rule is present in all of those. All right, this one's really friendly, but tricky if you don't know what it's asking. Definitely write this one down. So what do we have? They give us the function y, and I hope you can see right away that there's an outside function. The outside function is e to the x. Some people even like to put grouping symbols around there. And then the inside function is the 2x. So I notice a derivative here. It's actually the second derivative. There's a chain rule that we're going to have to apply. But the directions for this problem is basically kind of like a proof. Show the second derivative minus the 4 times the original function is equal to 0. So I've seen these questions appear quite a bit on like a short answer part of a AP test. So, all right, well, what do we need? I need to find these values. I already know what y is equal to. Right? They tell me, here is y. So if I'm going to start showing this, I'm going to plug y into that part. So I'll have 4 minus whatever y is. And then my goal here is going to be really what is the second derivative? That's going to go in this little blank space here. But let's plug with y with what we know about y. Y is e to the negative 2x. basically did substitution there, which means the work we have to do is we have to find the second derivative. Well, that's the chain rule. So I'm going to do this work off to the side. I'm going to take the derivative of the outside function. That's just the e. So the derivative of e to the x is itself with whatever is in the exponent. So derivative of the outside, keep the inside. And then I have to multiply by the derivative of the inside. So the derivative of negative 2x is just negative 2. And then I like to clean this up. So I'm just going to put the negative 2 out in front. All right, now that's the first derivative. If they asked me to use the first derivative in this, I would have to plug it in wherever it says that. But it doesn't. It says find the second derivative. So now I just have to find the derivative of the derivative. And notice it too is a chain rule. We have an outside function here. This negative 2 is a coefficient. That's just a multiplier. So we've got our outside function. And then I have the inside function again. So really, it's basically the same derivative with a multiplier of negative 2. All right, so I'm going to leave the original negative 2 out front. And then I'm going to apply the chain rule. I'm going to take the derivative of the e to the x. So derivative of e to the x is e to the x. We're going to keep the inside. We're going to keep the inside. And then I'm going to multiply by the derivative of the inside, which derivative of negative 2x is negative 2. And then that original negative 2 times the chain rule negative 2 can be combined together. And a negative 2 times a negative 2 is a positive 4, e to the minus 2x. So here's the second derivative. And we're just going to plug it right into the spot that we need it. And if you want to combine this together, you can to make it a little more clean, but hopefully you see you have positive 4 e to the negative 2x minus 4 to the e to the negative 2x. When we have the identical things subtracting, we prove that 0 is equal to 0. Okay. We did a couple of these really weird ones on the video from Wednesday. So if you didn't go back and see ones that had a product in a chain rule or a quotient in a chain rule, please go back and watch those. But look at this one. This one has a chain rule and then a product rule within it. So I'm going to give you guys a second. I want you to try your best at this. The only hint I'm going to give you to start is we have to do the chain rule first. Wrong color. So rewrite this. We don't like the cube root. How else can we write that algebraically so it means the same thing? But you're going to do the chain rule first. And then when you get done, you have the derivative of the inside, and the derivative of the inside is the product rule. So I'll give you about a minute and a half to see how far you can get on this. All right, let's take a look here. Now notice my notation. All I did was algebraically rewrite what it means to take the cube root, raise it to the 1/3 power. When I do that, that helps me really identify that here's a chain rule. We're going to take the derivative of the outside function, which is the 1/3 comes down, and then I'm going to take 1 away. And now a better way to write 1 in this case is 3/3. So I end up with a negative 2/3 in the exponent. So there's the derivative of the outside. Now notice I called this y prime using correct notation. Then we're going to rewrite the entire inside just the way it was. And here's the tricky part. Now I'm going to take the derivative of the inside, and that is the product rule. You do not have to show work for this. I hope we can kind of do it in our head. Notice we've got two functions. I've got 2x, and I have sine x. So the derivative of the first is just 2x, or excuse me, the derivative of 2x is 2. We're going to keep the original sign, and then we're going to add the original first problem, or first part, times the derivative of the second. And the derivative of sine is cosine. So here's the result of the product rule. The blue part is the result of the chain rule. And then just to clean it up, notice you have 1/3 as your fraction. This entire 2x sine is raised to the negative 2/3. So there's two ways you can do this. You just put all of this in the denominator to the 2/3 power, and then the entire product rule derivative is just going to be up top. Now notice this 1 would times all of this, so I really don't need the 1. And then I would just put 2 sine x plus 2x cosine of x. And I would be done right there. The only other thing they would do is, remember, raising this to a 2/3 power. The divide by 3 is like the cube root. And then the squared could go on the inside like this. So this squared is the numerator. The divide by 3 is the cube root. And then the original multiplier of 3 would just go out in front. So this is what the denominator could also look like. Your numerator would stay the same. The only reason why you need to know that is if it would be a multiple choice question. All right. I don't want you to write this one. Okay? All I want you to do is take a look at it, because every year there's a problem like this on the AP test. And it looks scary, it looks confusing, and a lot of kids kind of get lost in what's being asked. So what I'm going to actually recommend you do, before you even read, before you read anything, read the question. What is the rate of change of the percent of carbon-14 present in a 550-year-old fossil? Okay, so we've seen that word rate of change before. Now, if we were given 2 data points, that was slope. Right? Rate of change is just change in y's over change in x's. But in this case, you're going to learn a little bit in a little bit. The time is one single point. This is really your instantaneous rate of change, which all they're asking for is the derivative. All right, so now let's read and see what's actually going on. All carbon Earth contains some carbon-14, which is radioactive. When the living organism dies, the carbon-14 begins to decay at a fixed rate. The formula, here it is. This is the rate at which an organism decays. So it's 100 times e to the negative and kind of a crazy exponent, but this is just an e to the x with an inside function. So it gives the percentage of carbon-14 present at t years. So that's why we want to figure out how much percentage of carbon-14 is left over from a 550-year-old fossil. Notice that when t is 0, so if I plugged in 0 here, that would give me e to the 0, which is 1, is 100. So then that means at time 0, there's 100% of the carbon-14 present. That means the object probably just died, whatever it was, all living organisms. When the preserved body of a 15-year-old La Doncella and 2 of her children were found in Peru in 2005, they had 93.5% of the carbon-14 remaining in their bodies. Indicates that the 3 died about 550 years ago. Now, all of that you really don't need. It's kind of cool facts. What they're asking for is find the derivative of this equation and plug in 550. So that's all you would have to do for this. And again, I don't want you to write this down because we're going to have to use your calculator here, and I want to make this quick. So what do we need to do? We need to take the derivative. Well, to do that, I have to recognize the outside function is the e to the x. The inside function is right in there. So if I was doing this problem, this would definitely be a calculator question. I would write the derivative out. So I'd have the 100 would stay. Now we would take the entire exponent and we're going to drop it. Well, actually, I take that back. I want to set this up a little differently. We got to take the derivative of this. So the derivative of e to whatever was on the inside, there should be a 1 there, is itself, right? So we took the derivative of the outside, that's itself. And then I have to multiply by the derivative of the inside. Well, this is just t. So what's left over is right here. And I wouldn't clean this up. You could take the 100 and multiply it by this new constant. Now all you're going to do is grab your calculator and you're going to plug in 550 years, right where there was a t, and there's only one spot we have a t. And the only thing you have to be careful with is actually plugging this into your calculator. If you do it all in one step, you should have as many parentheses as I do. And then when you get that, that'll be your answer. Technically, you could stop here on a question, but then when you multiply it out, that answer needs to be turned into a percentage. So whatever answer you get, you would times by 100 to get its final answer. I don't want to take time just plugging that into your calculator. I think you guys can do that. All right, what I really want to do is get to our last problem here today. All right, now this is important. Definitely write this down. This is the idea, in my mind, of how calculus is going to play out for the entire year. We're going to have to use the rules that we learned. Maybe product rule, quotient rule, chain rule. And we have to apply them now to the context, the application side of this. So we're going to start off in pieces. What do we know? An object is moving horizontally, so that means it's moving left to right, and they give us the position equation. S of t is equal to negative cosine e to the 1/4 t plus 50, where t is equal to 0 to 4 seconds, and distance is measured in feet. So now we know that we're traveling for a total of 4 seconds from 0 to 4, and we know the position. So I could figure out, if I plugged in 0, I could figure out where this object started from. If I plug in 4, I could figure out the position at the end of the 4 seconds. But what I want to do is I want to find out how fast is the object moving. So we need to connect with that word fast, right? fast is going to imply velocity. All right, so what do we know about velocity? Velocity is the derivative of the position function. So I have to take the derivative of this function right here. Well, you may see the chain rule popped out here. I've got the outside function as negative cosine. And then I have an inside function, which is e to the 1/4 t, but there's actually another inside in that. That 1/4 is an inside. I'm not really worried about the plus 50. Remember, that's a vertical shift on the graph. So that just means that when I take the derivative, the 50 is going to go away because it's a constant. All right, so let's take the derivative of this function. We're going to start with this. What's the derivative of the outside? Well, the derivative of regular cosine is negative sine. So if I already have a negative, that's negative of a negative. That's going to give me a positive sine. And then we're going to keep the entire inside, e to the 1/4 t. And then I have to multiply by the derivative of the next inner function, which is just the e to the x. Well, the derivative of e to the x is itself. Keep the inside. And then I have to multiply by the derivative of the most inner part. The derivative of 1/4 t is just 1/4. Notice how I use multiplication, or I could even put parentheses. That's grouping all this together. Okay, so you could clean this up and rewrite it if you want. I actually think I'm going to because we're going to need it later on. But notice how I'm going to label this. I'm going to call it v of t because that's velocity. So the 1/4 would come out in front. 1/4. And then I would write the red e to the 1/4 t times sine. And remember, the inner part here, that's protected, so it can't move out. So there's my derivative, or that's my velocity equation. Well, now we've got to figure out how fast is it going at 4 seconds. So I'm going to plug 4 into this function. Look at my notation. I'm going to call it v of 4. And anywhere there's a t, I'm going to plug a 4 anywhere there's a t. Now this looks messy, doesn't look super friendly. Notice something. E to the 1/4 times 4, well, up top here, this gives me e to the first power. And then I've got 1/4 times 4. Well, that's sine of e to the first power as well. Now, technically, we could stop here. And I'm going to put my units. This is a rate of change. Well, what am I changing? I'm changing in feet per second. Okay? Well, this doesn't help me determine what directions it's headed. So I'm going to actually grab my calculator. and plug this in. So if you have a graphing calculator with you, maybe just give this a quick shot. Remember where the E button is? That's second LN. It's kind of the third button on the left of your calculator. And the reason why I'm showing you this, oh, you also have to make sure that your calculator is in Radian mode. So if you, right next to the second button is the mode, the third option down is degree or radians. Make sure it's in radians. Anytime you do calculus work, it should be radians. All right, if you type this in, I get an answer to 0.279. And in calculus, we always run around to at least 3 decimals. Okay? If it's your final answer, you can round to 3 decimals. If we're using that answer later on, we want to take all of the decimals that are given. So there's the speed at which we're going. We're going 0.279 feet per second, exactly at 4 seconds. So now you have to answer this question. What direction is it headed? And why? Well, the direction is based off of the fact that it's a positive velocity. So the object is moving forward, or you could even say to the right because it's positive. So moving forward, and then why? And all you have to state is right here. V of 4 is greater than 0. That's all you have to write because you already showed what V of 4 is. It's positive. Anytime it's positive, you're moving to the right or moving forward, or if instead we're going up, you'd be moving up. Okay, so the next question. When is the object at rest? We got to read that very carefully. What do we mean about the velocity when an object is at rest? If it's stopped, the velocity is 0. So now notice, this doesn't say plug 0 in. If I had plugged 0 into the velocity, that would be how fast is it moving at 0 seconds. We want to know when is the velocity 0 feet per second. So what I'm going to do then is I'm going to take the velocity equation and I'm going to set it equal to 0. And this is a little bit tricky with how we solve this algebraically. So hopefully you're really paying attention to this. When does the velocity equal 0? So if you were allowed to use your calculator, I would tell you to graph this and plug it into your calculator and just see when is it equal to 0. Well, let's pretend that you're not. What do we have? We have two functions that are being multiplied together. If they equal 0, that means one of them has to equal 0. This is called the zero product property. So our goal then is to solve for 0. Solve for t when the function is equal to 0. Let's do this over here. Okay, so here's the tricky part. We set the velocity equal to 0. We realized that it was a product, so we set each piece equal to 0. Now I'm going to solve for t. And I want to do this using proper algebra, so I'm going to multiply both sides by 4, which gets rid of the 1/4 in front, and 4 times 0 is 0. Nothing crazy there, right? Well, I'm going to actually scoot this 0 out a little bit more. Now I have to get rid of the e, and the only way to get rid of the e is to take the natural log of both sides, and that's a pre-calc term. So what happens then is the ln and e go away, and I'm left with 1/4 times t equals the natural log of 0. And here's the tricky part. If you type the natural log of 0 into your calculator, you get an error. The reason why is if you thought of the graph of the natural log, it never crosses 0. So you will get this popping up. This means it doesn't exist, which means I don't have an answer from this branch. So this branch cannot work. So I'm going to stop solving this here, and some people even like to put a little X through it. Okay. Now, I can solve this, and this is very tricky. How? How do we solve? I'm going to make the 0 pop out here just a little bit. How do we solve this piece right here? Well, inverse trig. How do I get rid of sine? I have to undo the sine on both sides. And this is the part that always kind of shakes my calculus students' core. The sine inverse and inverse go away. But then this part right here, how do I know what the inverse of sine is equal to 0? This is where I like to think of the unit circle. The question is really asking, when is the sine equal to 0? The sine of something is equal to 0 where? Well, what do we know? Let's think about this. On the unit circle, if I go over 1 up 0, don't we know the first value is cosine and the second value is sine? So when is sine equal to 0? It's equal to 0 right here at 0. Where else would it be equal to 0? This is the spot -1, 0. So you can see sine is equal to 0 here, and that's at pi. So I actually have two different answers. I've got sine is 0 at 0 degrees or 0 radians, and sine is 0 at pi. So now I have to solve these two, and notice it's the same work as we did over here. And you might actually notice this part is equal to 0. So if I take the natural log, I'm not going to get an answer for this part, but I will for this part. So I'm just taking the natural log of both sides here. That might be better to do it this way. This looks too messy. And then hopefully you're realizing that this is an error. So I'm not even going to bother solving this. This part is not going to result in a nice answer, but this one will. So if I take the natural log of both sides to get rid of the e, I just kind of want to sneak this in here. What's left over? The natural log and the e go away. And what's left over on this side is the natural log of pi. All right. And then our last step is to get rid of the 1/4. So we're just going to times by 4 to both sides. So very tricky. That stuff will come up. We'll see multiple times in that throughout the whole year. So if you didn't get it all right away, you'll have time to think about that. One thing I want to show you is this is just for the unit circle. So there was an answer at 0 that ended up in an error. But then as we go around, there's an answer here at pi. But what if I keep going around? Is there another answer at 0? And then is there another answer at the next time I go around pi? So the way that they compensate for that is they put a k, where k is any integer, and it just means how many times did I go around the circle. So if I went around twice, k would be 2. If I went around 3 times, k would be 3. But notice we're only doing this for the first 4 seconds, and pi is 3.14, so 4 seconds would be just past this. So the only true answer is what we have written in black. If there wasn't that domain, then we'd have to multiply by a k. All right, we're running out of time. I want to talk about this last piece. So we're not going to do this part, but what would you have to do? Well, if I asked you to find the acceleration, you take the derivative of your answer from before. So the acceleration is just the derivative of your answer to velocity. And then this last question is, what is the acceleration when the object is at rest? So what we would do is we take our answer from above, and we'd have to plug in when is the object at rest. Well, wait a minute, didn't we just find that? So I like this problem, and I wish we had a lot more time to explore it. You know when the object is at rest. You just found that time. So you would plug that answer into the equation that you got for acceleration. All right, so pretty heavy problems there, but I hope you kind of think of the derivative, the calculus of this is just the chain rule. The pre-calc is what makes it really hard. All right, so what do we have? Here's what I'd like you guys to think of. We have two things, and I'm trying to make this so it's as friendly as possible. One of the things I do want to stress here is this is an AP calculus course, and we don't meet every day, which means you guys don't get daily practice, and that's what we definitely need. So here's what I'm going to do to hopefully help this out. Today, you have a 10-question quiz that's on Delta Math. That is due tonight at 10 o'clock. All right, the quiz is titled 3.1 Chain Rule and Other Derivatives. Submit your screenshot to Schoology. Okay, so that's due tonight. By Sunday, you have 5 problems to work on. Okay, you've got these 5 problems in the textbook. I assigned 2 other ones that are optional, and I wrote those answers out. These answers are posted on the homework answer side in our Schoology page. So you'll see all the worked out solutions. This one is a really good one, 96. It's really quick and friendly. 98 is kind of like what we just finished. And then the other 3 should be very quick. The only other tricky part, 77A, the directions for that is on the page before. So you might look at it and think, well, what do they ask me to do? Turn the page to read the directions for that first problem. All right, that's all I got. We're done 10 minutes early, actually 12 minutes early, because I wanted to leave this open to answer questions about, are you missing anything? Do you have any questions from the previous homework on chain rule that we could look at? If you're feeling comfortable and you understand what's going on today, what's due tonight, and what's due Sunday, then you can leave. I got attendance, so you're good. If you'd like to stay on and get some questions answered, I could help you through that right now.